All right, in this video, we're going to look at some applications. So we're going to be looking at a problem dealing with the length of a circular arc. So I think it helps, first off, to remember that when we talked about what radians was, if you have an angle like theta and it's in radians, then it equals the length of the intercepted arc, which we a lot of times call S, okay, divided by the radius. And you can just say radius or the length of the radius just to emphasize. Okay. All right, now what we're going to be looking at is a formula for determining the length of the arc. So we want to solve this for S. All right, so if you have theta, let me write it again. If you have theta equals S over R, and you're trying to solve that formula for S, you can multiply both sides by R, and you wind up with S equaling R theta, and theta is in radians. Okay. All right, so we're going to make use of that on this problem right here. So first I want you to kind of have the picture in your mind. So here we have a circle. Let's see if I can get a decent circle. That's not too bad. Here we have a circle, not a great circle, but I'm not going to redraw it. It has a radius of 6 inches, which means this right here is 6 inches, okay? And then we want the length of the arc intercepted by a central angle of 45 degrees. So here would be the location for that angle. All right, and we want to know this right here. All right, so this length of that arc. So that's what S is, the length of the intercepted arc. All right, so we want to use the formula. So we know the formula. We know the formula is S equals R theta. And we know the radius is 6, so we can put that in. The thing is, when we go to put in the theta, we need theta in radians. So we're going to take a moment to take 45 degrees, and we're going to think about it. We're going to change it into radians. So you can do it by remembering that conversion fact that pi radians is 180 degrees, and we put the 180 degrees on the bottom because we want the degrees to cancel out, right? And then we just simplify. So 45 goes into 180 4 times, and so we wind up with 45 degrees equaling pi over 4 radians. So you need to be sure that your theta is in radians. So then you're going to come back over here, and where theta is, you're going to put pi over 4. And so you know the length of the arc would be 6 times pi over 4. Okay, so that's 6 pi over 4. That's 3 pi over 2. And the unit on that would be in inches. I know we say radians there, but actually it's since theta in radians is the length of the arc divided by the length of the radius, your units are actually completely canceled out. And so you wind up having a unitless quantity. And so this 6 right here being in inches is why this turns out to be 3 pi over 2 inches. And then get used to being able to get the decimal form of that, because sometimes we want the decimal. So if we wanted that to say the nearest tenth of an inch, we would type 3 times pi divided by 2, and we would get around 4.7 inches. Okay. All right. Now, we're going to do a problem that looks at linear and angular speed and their relationship. So I want to kind of develop the formulas for that. All right, so let me get this to be up here a little bit more. So this is 3 pi over 2 inches, which is about 4.7 inches. And let me get rid of this right in here so I have room. Okay. Now, Trying to erase. All right, so let me get to the linear and angular speed formulas. All right, so let's take a look at these. All right, so when you're looking at the linear speed, that's the velocity that something's moving. For the linear speed, okay, a lot of times we use v for that, it's velocity. It would equal your movement along the arc, how far you went around the circle on the arc itself, divided by the time it took you. It's kind of like distance equals rate over time in a way. S is like the distance. Okay. All right, and then for the angular speed, you're looking more at the rotation. Okay, so the angular speed, a lot of times we use a little w for that, would be looking at the amount of the rotation divided by time. Okay, and on here, be sure, and also on the top one, on this problem and this problem, be sure theta is in radians, not degrees. Got to do that conversion first. Okay, so make sure you do that. All right, now you can look at the relationship in the two by thinking about that arc length formula. So remember the formula S equals R theta that we developed earlier? If I divide the left side and the right side by time, we get a new formula that relates the linear and the angular speeds. See, the S over T would be the velocity. Okay, so that would be replaced, could be replaced with V. And then the theta over T can be replaced with W. So we have V, that's a V, equals RW. And that would be the relationship between linear and angular speed. Okay. All right, so now let's see how we can use this to solve an application problem. And so you think about this. We have a Ferris wheel. Okay. And so your Ferris wheel has a radius of 25 feet. Okay, so that means the radius is 25, no matter where you are, that's 25 feet. Okay. The wheel is rotating at 2 revolutions per minute. Okay, so that means it goes around once, and then it goes around a second time. Okay, and it does that in 1 minute. And your job is to find out the linear speed in feet per minute of a seat on the Ferris wheel. So you can kind of imagine somebody just kind of sitting right here. So how fast are they moving along the edge of that circle, around that circle? That's what you're looking for, okay? So one of the things to watch out for, it didn't happen here, is to make sure that your radius is given to you in the proper unit, and it was. And then to remember how these formulas, when you use them, you need to be dealing with theta in radians, okay? So I notice I have something that sounds kind of like an angular speed. You know, when it said 2 revolutions per minute, 2 revolutions in 1 minute, I like to start there and just use my dimensional analysis like I did when I was converting back and forth between degrees and radians. Then I can think about this, and I know that 1 revolution is 2 pi radians, right? 1 full circle around would be 2 pi radians. So if I did that, that would get me from revolutions to radians per minute. You see that? And so I wind up going 4 pi radians per minute. Okay. All right, now I can go to the formula. I'm trying to find the linear speed. And so I can use the formula that relates those two. And I know the radius is 25. So in place of r, I'm going to put 25. And that 4 pi radians per minute, that's the angular speed. So that's the 4 pi right there. Okay, so I can multiply those two, and I get 100 pi. Okay, and this was in feet. And even though I do say radians, really it's a unitless quantity. This would just be per minute. Okay, 4 pi per minute. So it would be 100 pi feet per minute. Okay, and then if I work that out, if I took the 100 times the pi, it would turn out to be about 314 feet per minute. Okay, that's how fast you're going. Okay. All right, so that ends the section 5.1. So if you haven't yet, you want to get in there and really start working on those problems.